Okay, so what we're going to talk about now is something called an orthogonal projection. And probably you've seen an orthogonal projection before. If you've done work inside of multivariable calculus, I would say that you've definitely seen this before, probably inside of the first chapter of your multivariable calculus class. Because the idea here is that we're going to utilize our standard inner product space. We're going to use our dot product, and we're actually going to answer a question. And answer a question, again, that you've actually probably answered before. Okay? And that is, what is the shortest distance between a point and a line in Rn? So by answering that question, we'll actually get our definition of an orthogonal projection, and this will help us out quite a lot, okay, in terms of answering, like I said, answering this question. So let's imagine that we've got a line, we'll call it L1, okay, and we've got a point, we're going to call it P of x naught, y naught, okay, and we're going to define L1 utilizing a vector equation, R of t, and that's going to be equal to V1, or excuse me, that's going to be equal to some vector v times a parameter t plus a point, we'll call it q, and in this case we'll just call it q, and it could be x1, and it'll be x1 y1, because we're looking in 2 dimensions. Now here's the thing, we could actually work in n dimensions in order to solve something like this. It doesn't actually matter how many dimensions we have. The equation for a line, okay, is always going to be this equation right here, right? And, you know, and so if we have a single parameter, we define a particular point, right? We've got this direction vector that gives us the definition for our line, all right? So what I want to imagine is that I've got, we'll call this q of x1, y1, all right? And then here's v, and v is this direction vector. And so we're just going to imagine that it's out here. There's v, the direction vector. All right. Now, the shortest distance between P and line L is going to be a perpendicular distance. So it's going to be orthogonal. So we've got this orthogonal distance there. And what we can do is we can say, okay, so let's draw a line, all right, or draw a vector. And that vector, we're going to call it W. All right. And so W is just going to equal x naught, or x1 minus x naught, comma, y1 minus y naught. And if we have, you know, if we're in a different space, different dimensions, you're just going to like develop a vector. But we're doing it in 2 dimensions, so that's why we've got the specific number. Okay? And so consequently, what we have here now is we have a right triangle. And so what I want to do is I want to imagine, okay, what I'm going to do is I'm going to squash W onto V. Okay, I'm going to squash W onto V. So I've got W, I'm going to squash it onto V, and essentially the horizontal part, this part right here, that vector right there, okay, is going to be, it's called our orthogonal projection. All right, so our orthogonal projection is the horizontal component of W, all right, essentially of W onto V. Now, if it was, you know, if V was actually, if V actually ended up being, you know, a, on, say, for example, the x-axis, then it would be very simple. I mean, you just take the x value for W. But in this case, we're going to assume that it's not, okay? So we've got to figure out what that's going to be, all right? And we're going to call that P of WV. Now, what you may have seen it as rewritten as P of V, okay? And so basically that's we're going to say it's W onto V, and that's W onto V. W is the thing that we're projecting down onto our vector V, okay? You may have seen something like that. All right, so now let's look at how do we figure out what that vector actually is. So one piece of information, we'll come back to this in a minute, is that P of WV is in the same direction as v. So P of WV is in the same direction as v. Okay? They just have different magnitudes. All right? So basically, P of WV is a scalar multiple of v of some sort. Here's W. And then this length, which is actually what we're looking for. Remember, we want to find the length of the distance, that distance from P onto L. This length here is going to then be P, is going to be W minus P of WV. Or that's what that vector is, and its magnitude, okay, the magnitude of W minus P of WV is the distance we're looking for. Okay? So what we're going to do is we want to figure out how long is W minus P of WV. So first we want to figure out how long is P of WV. Well, we've got an angle here, theta. Okay? And we remember that P of WV is in the same direction as V, so we do know actually a relationship for theta. Okay, so first piece of information we have here is that W dotted with V is going to equal the magnitude of W times the magnitude of V cosine theta. All right, so you got that from your multivariable calculus class. We also talked about that with the Cauchy-Schwarz inequality. Okay, this ends up becoming one of those powerful results there. All right, and in addition to that, right, and that kind of makes sense, or, pardon me, and so what we have too is that means we also know that P of WV, okay, its magnitude is going to equal the magnitude of W times cosine theta. And that's because, right, because P of WV is the horizontal part of that triangle. Right? So if you think back to your trig, we know that if we take the length of the hypotenuse, we multiply it by cosine theta, what we do is we get the length of the horizontal part. All right? So now what I'm going to do is I'm actually just going to do some algebra. I'm going to first take equation 1, equation 1, equation 2, and we're going to then divide through by those magnitudes. So the dot product of W and V divided by the magnitude of W, magnitude of V, is going to equal cosine theta. I'm going to change my notation, by the way, and I'm going to utilize this notation so that we can actually talk about it in terms of any unit product. And so that's cosine theta. Okay? So the magnitude of orthogonal projection is going to equal magnitude of W times the dot product, or the inner product of W and V, divided by the magnitude of W times the magnitude of V. And thus, that's going to end up equaling the dot product of W and V divided by the magnitude of V, because we can just cancel these two. Okay? All right, so that's actually the magnitude of P and WV. Now, something to remember here is that if we want to find, right, so for finding the finding a vector in a particular direction. So we want to find a vector in a particular direction with a particular magnitude. And so we'll let the direction be v with a particular magnitude. And our magnitude in this case is going to be this WV divided by the magnitude of v. Okay. What we do is we normalize. So we make unit v. We're going to normalize v and multiply it by the magnitude. Okay, so kind of remember that from your multivariable calculus class. So what we're doing here is we're going to normalize v. That is, we're going to make a unit. Okay, so now it's got a length of 1, but it's still in the same direction, but length of 1, and then we'll multiply by our magnitude, And when we do that, we end up with a vector that actually has the right magnitude and is in the right direction. Well, our direction here for P of WV, right? So we want to say P of WV then is going to equal, we know its magnitude, this was its magnitude, WV over the magnitude of V. And then the direction then as a unit vector is going to be V divided by the magnitude of V. All right, so that's now V normalized. And that then is going to be the inner product of W and V over the magnitude of V squared times V. There we go. All right. And so if we look at this, this kind of makes some sense. All right. So what we've done is we've got, here's the L1 has its direction, and its direction vector is V. Okay. And we also know that, so what we're going to do is we're going to create an orthogonal projection called P of WV, which is in the direction of V. All right, same direction. And then we went out and we said, okay, well, we utilize some information that we know about the inner product in order to give us the magnitude of P of WV. And that's WV over the magnitude of V. That's its magnitude for the projection. All right. And then we'll multiply its magnitude times the normalized vector V over the magnitude of V. So this is unit times its magnitude, and that actually gives us the orthogonal projection. So make a note of it. This is the equation for the orthogonal projection. All right, so we've actually then gone in and figured out what that would be. Now what we're going to do is we're going to find something called the component, which is W minus P of WV. Okay, well, let's take a look at that. Let's what that means, like once we found P of WV, then all we need to do is we take the equation for W minus P of WV, okay, and its magnitude is the distance from the point to the line. So we're going to use this process. I know there is actually another process that you can use, and there's actually a formula that you can use. What I want you to do is I want you to do this because we actually need to work on finding the orthogonal projection. It's going to end up becoming very important for us for the Gram-Schmidt process, so I do really want you to practice it. Okay? So, let's take a look. Let's do a problem. So let's take a look at an example. What we want to do here is we want to find the distance from P of 9, 0, negative 4 to the line L that has a parametric form of x of t equals negative 3t, 1 plus 6t, negative 1. So remember, what we're going to eventually want to find is we're going to end up finding W minus P of WV. And we're going to want to find its magnitude. So we need to find W, we need to find P of WV. Okay? So the first thing that I'm going to do is I'm going to rewrite L. And L, we're going to call it x of t. We can rewrite x of t to equal, and we'll have our direction vector is going to be negative 3, 6, 0, t. Right? Because you can see the coefficients for x, for y, right, and z are negative 3, 6, and 0. Plus, and then we'll have this point, and this point's going to end up being q. This will be 0, 1, negative 1. Okay? So if I draw my picture, essentially I'm going to have L, right, and I'm just going to draw it flat for the sake of ease. L here is going to have, here's my direction vector v. V is going to equal negative 3, 6, 0. Okay. We'll have Q, we'll define Q as being 0, 1, negative 1. And then we have P up here as 9, 0, negative 4. And so this thing here, that vector, is going to end up being W. Okay, there's W. So W, we'll first find that, is going to equal 9 minus 0, 0 minus 1, and negative 4 minus a negative 1. Right? I know it's not in the right position. It's fine. All right? We're just demonstrating. So this ends up being 9, negative 1, negative 3. And there's W. And so now we need to find P of WV. And so we've got an equation for P of WV is going to equal W dotted with V over the magnitude of V squared times V. Okay, so there's P of WV. So W dotted with V is then going to be 9, -1, -3, dotted with -3, 6, 0. And that's going to end up equaling -27 minus 6 plus 0. And that thus is going to equal -33. The magnitude of V squared is going to equal then -3 squared plus 6 squared. And so plus 0 squared. And that thus is going to equal 9 plus 36, so that's going to be 45. So the magnitude of P of WV, okay, or excuse me, not the magnitude of P of WV, but the P of WV is then going to equal, it'll be -33 over 45, right, times -3, 6, 0. Okay? And so if we simplify that, what we'll end up getting is we're going to end up getting 11/5, -22 over 5, and 0. And so that is, in fact, P of WV. Now what we need to do is we need to find W minus P of WV. And so consequently, what that's going to be is that's going to be 9, -1, -3, minus 11/5, -22 over 5, 0. And so that's going to end up equaling, that'll end up giving us, okay, it'll be end up being 34 over 5, 17 over 5, and -3. We take the magnitude of W minus P of WV, okay? Plug that into your calculator, and what you'll end up getting is you'll end up getting the square root of 1,670 divided by 5, which ends up equaling, it's approximately 8.173. Okay? I know it's a little bit of an involved process, especially if you're kind of used to equations, but we actually kind of want to understand where the orthogonal projections are coming from. So this is the method that I actually want you to use. All right, so I'm going to have you use this, and if it comes up on an exam or something like that, you're going to use this method. All right, you're going to find that orthogonal projection, you're going to find W, okay, and then use that in order to find the magnitude of W minus P of V. So now what we're going to do is we're actually going to go in and we're going to start thinking about orthogonal projections, but we're thinking about them now from the perspective of maybe like we're working with a plane. We've got a plane in space, some Rn space, and we want to find the minimum distance from a point to a plane. So I want to imagine that I've got this plane, okay? So here's my plane, and here's my point, call it P. P, and, you know, call it P of X naught, Y naught, Z naught. How about that? Whatever. Doesn't really matter. And so, actually, let's just call it P. Because what we want to do is we want to think about this from like any n-dimensional space. And so what I do know is I know inside of my equation for a P, for the plane, I'm going to have this vector. It's going to be, right, it's our normal vector, and the normal vector is perpendicular to the plane. Okay? Right? So this is n, that's my normal vector. I can actually imagine that I've got n coming out of here too. Okay? So we've got some normal vector coming out there. I'm sorry, it's not as clear as it is. I've got P here. Okay? And what I want to imagine is like, let's say, for example, this is Q right here. There's Q, okay? And so I can draw a line from Q, right, out to P. Let's say there's P right there, okay? And here's N. And then I've got this line right here as well, okay? And that's a right triangle, okay? So I've generated a right triangle. Actually, this here is also kind of like, this would probably be, yeah, so there we go. Right, I've got this right triangle, and this thing here, this is our vector W. Okay, so there's our vector W. And if you remember how orthogonal projections work, an orthogonal projection is we're just going to take W and we're going to pop it onto N. All right? So N's in this direction. We'll just imagine that N might be a little bit longer. And this thing right there, that length is P of W projected onto N. So it's P of W. It's the orthogonal projection of W onto N. All right? And so the magnitude of the orthogonal projection onto N is the distance from P to the plane. So if you just imagine, because like essentially that N vector, right, is running parallel to another vector that's also orthogonal. Okay, we got another orthogonal vector right there. Okay, so P, that's the perpendicular distance from the plane to P. That's going to be that shortest distance. Okay, and that's the shortest distance. So what I got to do is I got to figure out what P of Wn is, or at least what its magnitude is. Okay, well, I already know what it is. I know what its magnitude is. The magnitude of P of Wn is going to be W dotted with N over the magnitude of N squared. Or not the magnitude of N squared, just the magnitude of N, pardon me. The magnitude of N. And that's from our earlier equation, right? Or that's the inner product divided by magnitude of N. And that is the magnitude of P of Wn. So that's actually the distance that we're looking for. So in this case, it actually is a little bit easier if I actually know the magnitude of N. Well, I do know the magnitude of N. Because the magnitude of N, or excuse me, not the magnitude of N, pardon me. I do know what N is. If I have the equation for the plane, N is just simply the direction vector that goes into the equation for the plane. All right, so now in order to continue with our work, we're going to need some information. So one, we're going to recall that we have the equation for a plane. So a plane is going to be AX plus BY plus CZ plus D equals 0. Okay? And the way that plane gets constructed is that my normal vector, N, is going to equal A, B, C. Okay? So basically the coefficients in front of X, coefficient in front of B, coefficient in front of C. Now, we're going to have Q, and we're going to define Q here as X1, X2, X3. So Q is going to be X1, X2, X3. And then remember P is now, we're going to define that as X0, Y0, Z0. So X0, Y0, Z0. Okay? And so what we'll do is we'll find P minus Q. So P minus Q is going to end up equaling W. That's the vector W, which is going to equal X0 minus X1 plus, or excuse me, and then Y0 minus Y1, Z0 minus Z1. Now we'll use our projection, this equation right here, and we're going to say, okay, well, let's first figure out, we want W with N, not V, but W with N. So we're going to take the inner product. We've got X0 minus X1, Y0 minus Y1, Z0 minus Z1, dotted with ABC is going to equal A times X0 minus X1 plus B times Y0 minus Y1 plus C times Z0 minus Z1. And then the magnitude of N is going to equal the square root of A squared plus B squared plus C squared. Okay? So what I need to do now is I'm going to notice some things, okay? I'm going to notice that here's the equation for my plane. AX plus BY plus CZ equals 0. So if I rewrite, here's my here's my dot product, okay? So I've got ax naught minus ax1 plus by naught minus by1 plus cz naught minus cz1, okay? It's going to end up equaling ax naught plus by naught plus cz naught minus ax1 plus by1 plus cz1, okay? Which, by the way, right, this is essentially, it's the normal vector times q, okay? Now, here's what I want to see, okay? So I know, I'm going to do a little bit of extra work into here. I'm going to say, okay, well, I know that ax plus by plus cz plus d equals 0. And I know that q is on the plane. So q, x1, y1, z1 is on the plane. Okay? So what I'm going to do is I'm going to plug in x1, y1, z1. I'm going to get ax1 plus by1 plus cz1 plus d equals 0. So what that means is that negative d is going to equal ax1 plus by1 plus cz1. Well, what we want to notice is that this thing here is actually equal to that thing there. All right, so it's negative d. So what we get here is that that dot product, this dot product right here, is actually equal to, so w dotted with v is equal to ax naught plus by naught plus cz naught minus a negative d. Okay, which we're just going to end up being plus d, right? So the magnitude of p, w with n, w with n, which is the distance that we're looking for, is going to equal the absolute value of ax naught plus by naught plus cz naught plus d divided by the square root of a squared plus b squared plus c squared. And that actually ends up being the equation for the minimum distance between a point and a plane. All right, equipped with an equation now, this should be not too much of a problem. So let's say, for example, we want to find the distance from P, -4, 7, -2, to the plane x plus 2y minus 4z minus 2 equals 0. So first, what we're going to notice is that we're going to have A is going to equal 1, B is equal to 2, and C equals -4. Okay, that's the equation for a plane, right? We have the ax plus by plus cz, and then d is going to equal -2. All right, and then we've got x naught, y naught, z naught, which is our point P. So my distance, P of w n, right, the magnitude of that orthogonal projection is going to equal the absolute value of 1 times -4 plus 2 times 7 plus -4 times -2 minus 2 all over the square root of 1 squared plus 2 squared plus -4 squared. Do a little work here. We get -4 plus -4 plus 14 plus 8 plus minus 2. So that's 22, 20, 16. So it's going to be 16 over, and this will be 1 squared. So that's, this is going to be 16, 20, 21. So it's going to be 16 over the square root of 21. And that is our distance. That's just, I just want to check. Right? 4, 10, 16. Okay, great. And 1 squared. And there it is. 16 over the square root of 21. And that is our distance. Look at that. Not so bad. All right, so what we did here inside of this lecture is we actually talked about orthogonal projections. And I do want you to go through, I want to make sure that you're watching the video. For those of you who are in my class, if you're actually in my class, we are going to use, you are going to use this method in order to find the point, the distance from a line to a point. Okay, so you're going to find W, you're going to find the projection, and then subtract the two of them and find its magnitude. That is actually the process, because I'm interested in the process. I'm not actually interested in the result, right? The result, there's an equation for it. It's nothing too difficult, but like I'm really interested in the process, right? Okay. And basically this whole idea of an orthogonal projection is going to allow us, okay, it's going to become one of these things that we're going to be utilizing in order to find orthogonal sets of vectors, all right? So we're going to use this in something called the Gram-Schmidt process to find orthogonal sets of vectors, all right? And so that actually finishes up our lecture.